Let's take a look at example number 2. Aqueous ammonia is mixed with nitric acid. So, what does that look like for us? What are the entities? What are the potential acids and bases? Or what are the strongest? And we go from there. So, ammonia. When we remember ammonia, that is NH3. All right, NH3, you see nothing but nonmetals there. So therefore, ammonia is molecular. With the molecule of ammonia, it would just dissolve and go into aqueous state. So we have NH3 aqueous as a potential entity. On the other side here, it's not mixed with water, it's mixed with nitric acid. And so nitric acid is HNO3, another molecular compound, but we need to figure out for this acid, is it one of the strong or is it one of the weak? When we take a look on our table here, we see that nitric acid is one of our strong acids, which means it will react completely with water to produce hydronium and its associated anion of nitrate. So this would not exist in water. It would form H3O plus, NO3 minus in solution. All right. Finally, we do have solutions of these guys, so we should remember that water is a potential player. Now what we're going to do is we're going to go through our list and we're going to look for all of the potential acids and bases. Please pause the video and look for those entities in your 2 columns and list all of your potential acids and bases. Do that first, see what you come up with, restart the video again in a few minutes, and I will take you guys through how I found all of the various ones. Okay, so here's our various entities. All right, I'm going to look for ammonia first. Let's see if I can find that anywhere. I doubt very much it's going to be on the acid side, just because I know ammonia from Chemistry 20 was one of our bases. I see something close here with ammonium, but I don't see ammonia, so I start looking on the other side, and oh, lo and behold, there's ammonia. It is a potential base. Hydronium, that's our atypical acid character, so I'm pretty sure it's going to be here on the acid side. All right, one of the strongest potential ones. There's your acid. We want to look for nitrate. All right, if you look for nitrate, it is up here in the strong acid and conjugate base side, which technically means it can behave as a base, but being that these are quantitative, it has to be a pathetically weak base and really just not something that can sustain a reaction. So whether you include it as a base or not shouldn't really affect your list of entities. Stuff that's up here on the strong side shouldn't really play. Water, we already know, is on both sides, so it is a potential acid and a base, and so we can employ that shortcut like we've done with electrochemistry, where we just know water is a potential player on both sides of the table. What we're looking for now is which is the strongest of the 2 acids between water and hydronium. I don't think I need a drum roll here to highlight which one is the strongest, but we'll show it again anyway. Hydronium is here near the very top of your table. Water is down at the bottom of your acid table, meaning that hydronium is the strongest of the 2 acids. We have 3 potential bases, and so we should take a look at those. You have nitrate, which is the conjugate base of a strong acid, should not play. Water, which is a very weak base. And then down here, actually quite near the bottom, we have ammonia, which would be near the strongest of the bases. So ammonia now is our strongest base. Remember that the proton transfer is between the strongest acid and the strongest base. So we can predict our products. Or pardon me, predict our reactants. So, if you want to take a look at the reaction, the strongest acid we had was H3O, and our strongest base was the aqueous ammonia. This should exist in equilibrium. We just have to find that proton transfer. Remember, this was our acid, our proton donor. This is our base, our proton acceptor. So the hydrogen should move this way. This allows us to predict our products. Hydronium gives up a hydrogen. All that would remain would be liquid water. And if ammonia gains a hydrogen, it would have 4 hydrogens rather than 3, and it would contain a surplus positive charge. Okay, and so there is our products predicted by the Bronsted-Lowry acid-base reaction. We do want to take a look at strongest acid versus strongest base. Your strongest acid was hydronium. Your strongest base was way down here as ammonia. That is a big downhill lie. And so remember from our spontaneity or equilibrium table that if your strongest acid is above your strongest base in the table, then you will have a product favored or greater forward reaction in this particular case. And so we conclude the position of equilibrium here and realize that we're going to have much more ammonium and water in this reaction than we will hydronium and ammonia because of the relative strength of the 2 acids and the 2 bases. Okay, I hope that one made sense to you guys. The next example is going to take quite a bit to get through, so I'll have to do that in yet one more video. But what we can do here is, using the information we have about relative strengths, we can build our own acid-base strength table, much like we built our own reduction tables back in electrochem.